we're going to be moving into the mathematics that was the result of the calculus that was done. And we're not looking at the calculus. We're just going to be looking at the results. And this is the mathematics that you want to focus on when the questions deal with time and either molarities or partial pressures. The difference is time rather than rate. Really common to see a molarity, to see a time, and try to mathematically conjure up a rate. Don't give in to that temptation. We have math formulas that have already taken care of that for us. Now, these are the math formulas that we have. These are called the integrated rate laws. And I'm going to focus on concentration, but you could certainly do partial pressures as well. Now, this that we're doing right now, this is what relates to the crystal violet lab that you did before Thanksgiving, and you haven't written up yet because you didn't know how. So you have the data. Now I'm going to be showing you how to write it up. So if we take a zero order, and we're talking about just a single substance right now, I'll address what we'll do if there's more than one substance. We're talking about one substance. If it's zero order, the calculus gives us this equation. And we would graph the concentration of our substance versus time. And if we did that, we would get a straight line. And you notice that that straight line has a negative slope associated with it. So we get a straight line, a negative slope if we did molarity versus time. Now, the slope is equal to negative k. So if we take the slope, if we can determine the slope from the value of the slope, we set that equal to minus k, and we can solve for a rate constant experimentally. So this type of mathematics is used for a variety of things, but the graphical method can be used to check for order and also to determine a k value at a given temperature. So the next one, we have the natural log. It just is the way the calculus works out. And we would graph the natural log of A, so natural log of our substance A at the varying times that we have. And we're going to again get a negative slope. So we'll graph that against time. Now the intercept you see is the natural log of the initial concentration. It's typically not the most interesting thing, but that is something that you should know, that as we extend the line back to time equals 0, that would be the natural log of our initial. Typically we know our initial, but not always. So, and we have a similar concept here. If we took it back to there, this time the intercept equals the concentration at time equals 0. Now again here, my slope is equal to minus k. So, and then finally, this is for second order. We graph the inverse, and I hope you're figuring out now that you have to know what you need to graph to test for which order, and you need to know that the slopes are negative, negative, positive, and you need to know that how you would get k from that slope, so that if we get the slope here, in this case, the slope directly equals k. Now, you'll need to know all of that information to be able to determine that. So what do we as scientists do? Well, we test these graphs. So we do a graph test, and I'm going to do that. I'm actually going to be trying out Camtasia for the first time with you. This is what you're going to do with your crystal violet. We'll make 3 different graphs, and we'll try to determine which one of these correlates. Does our data correlate to a straight line for that y? Does it correlate to a straight line for that y or for this one? So whichever one gives us the best correlation coefficient is the one that we would say, hey, this is the order. And I'm going to be doing one with you here in the next video. So this gives you some examples to look at, and they're not the same ones, but it just lays it out for you fairly clearly that what we're graphing here. And you would need to look at that and recognize that this is a 0 order graph. And you would have to be able to tell me that I could get my rate constant from the slope. Now in this one, if the graph looked like this, with that being natural log, if it was a straight line, you need to be able to tell me that that's a first order and that the slope is equal to minus k. And if we graphed 1 over our concentration, we'd get a positive slope. That's very critical. Negative slope, negative slope. That we'd get a positive slope, and we get k right from the slope, and that this represents second order with respect to that substance. Now, what do we do then if we have more than one reactant? I mean, that's fine if it's some substance that just is, 2A going to product, and I only have one substance that's either, 0 first or second order, but, that's not always reality. What we can do is set up a situation that we call a pseudo rate law expression. What a pseudo rate law does is it, focuses in, we focus in on one reactant. This is what you did in that crystal violet lab. Okay, and I'll use that as an example. So we're going to focus in on one reactant. We're going to use in the lab, as well as you're going to do it in WebAssign and so forth. We're going to use the graphical method. We're going to do all 3 graphs and test to see which is the best straight line. Now, let me see if I can explain this better with an example. In ours, you took crystal violet and you reacted it with hydroxide and made a product. I'm not really concerned about that right now. Now, we started, let's say, with 2 times 10 to the minus 5th molar of this. I don't remember the exact molarities, but it's going to be on that order. And 0.1 molar of that. So what we did is we made our hydroxide much, much greater than our crystal violet. So let's take a look at this halfway through the experiment. If I've lost 1 times 10 to the minus 5th, and this is a 1 to 1 mole ratio, that means I've also lost 1 times 10 to the minus 5th of my hydroxide. So a rice table we're going to be using for stoichiometry as well as other things, and we call this an RIC, and I like to put end if I'm dealing with a stoichiometry. So I would have 1 times 10 to the minus 5th here. Well, 0.1 minus 1 times 10 to the minus 5th is pretty darn close to 0.1. So what that means is that the concentration of hydroxide in our case was held constant. So we have this constant and that constant, and what we do is we wrap them into one constant. So our second reactant is hidden in this new K that we call K prime. All a K prime is we're distinguishing one K from another K by putting the prime there. Okay, so now that narrows it down in our case to rate is going to be equal to a K, a pseudo rate constant, if you will, times our concentration of our crystal violet to some order. And we'll need to do 3 graphs to determine what that order is, the best part of that. And that's what we're going to be doing next. So I'm going to be shifting over to test out Camtasia. And until then, this is, as always, teaching you with lots of love.